Hello everyone, myself Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Abhidayanangar Senior College. In the subject Mathematics, Groups and Coding Theory is very important paper. Now in Groups and Coding Theory, already we have seen the first unit. Now we start with the second unit, that is Groups. Now in groups, we have to study these 3 points: binary operation, second group definition and examples, and third is elementary properties of group. Now first is binary operation. Let G be a non-empty set, then the set G cross G is set of all ordered pairs A, B, where A and B are members of G. A binary operation F on a set G is a function or mapping from G cross G to G. That is, a binary operation on a set G is a function that assigns each ordered pair of elements of G a unique element of G. Now see what is actually a binary operation on some set G. Now first of all, G must be a non-empty set. Then G cross G is nothing but the Cartesian product of G with itself. So it contains all the pairs A, B, where A and B both are members of G. Now, if we define some function f from G cross G to G itself, it means what? We have to apply that function f on every element A, B belonging to G cross G. Then whatever is the element f applied on that A, B is a unique element of G. Then we say that f is a binary operation on that set G. Now, whenever f is some binary operation on set G, G is called underlying set, and that mapping f is called as a binary operation on the set G. In other words, we say that G is closed under f. Now, instead of using f, we use the symbol A star B to denote f applied on that A, B. Now, to clear the concept of binary operation, we see some examples. Addition is a binary operation on the set of integers z. That is, addition means plus. It is defined from z cross z to z. Because if we take any two integers, say a and b, and apply rule of addition on them, that means we apply that function plus on every pair of z cross z, then the resultant element a plus b is again an integer. That is, a star b equal to a plus b is present in z and is unique for all ab belonging to z. Actually, in short, it means what? If you are considering any two integers, then their addition is again an integer and it is a unique element. For example, if I consider 2 and 3, both are integers, then 2 plus 3 is 5, which is again an integer, and that addition element is unique element. If I consider 8 and minus 5, both are integers, and their addition 8 plus minus 5 is 3, which is again an integer, and that element is unique. So in this way, if you consider any pair of integers a and b, then in that case a plus b is again an integer and it is a unique element. So we can say that addition is a binary operation on set of integers. Now, similar to integer set, if we consider Q, the set of rational numbers. What is set of rational numbers? Set of rational numbers, it contains all elements of the type P divided by Q, where P and Q are integers and Q not equal to 0. It means it contains all the fractions. So, all integers are present in rational number set, because if you consider any non-zero integer a, then you can write it as a divided by 1 in the form of fraction. So all integers are rational numbers. Together with all integers, the fractions of the type 1 by 2, 2 by 3, all these are present in rational number set. So if I again define addition on Q, then addition is defined from Q cross Q to Q itself. Why? Because if you consider any two rational numbers, say A and B, and if we add them, then A plus B is again a rational number and it is unique. So addition of two rational numbers is again a unique rational number. And so addition is a binary operation on rational number set. Similar way, addition is a binary operation on real number also. So real number is nothing but set of all rational numbers together with all irrational numbers like root 2, root 3, pi, e, etc. So if you add any two real numbers, then again we get a real number and it is a unique number. So addition is a binary operation on real numbers. So remember, addition is a binary operation on natural number set, then integer set, then rational number set and real number set also. Now see multiplication. So just check, if you multiply any two integers, then what is the answer? So again it is a integer and it is a unique number. So multiplication of two integers is a unique integer. So we can say that multiplication is also a binary operation on Z. Similarly, multiplication is a binary operation on Q, means rational number set, and R means real number set. Now next consider the set M by N R. So this is the set of all M by N matrices with real numbers, real entries. So what is matrix? So matrix is nothing but the arrangement of numbers in rows and columns. So M by N matrices means there are M rows and N columns, and all the entries of matrices are real numbers. So that is the set M by N R. Now, matrix addition is a binary operation on this set, because if we consider any two members of M by N R, means any two matrices, say A and B, in that set, so both are M by N matrices with real entries. Then star means matrix addition is A plus B. So addition of two M by N matrices is again an M by N matrix. So order of resultant matrix is M by N. And as we are adding real number with real number, the resultant addition is again a real number. It means for any two combined real matrices, their addition is again a combined matrix with all real entries, and that matrix is unique. So we can say that matrix addition is a binary operation on M combine R. Now see subtraction. Subtraction is not a binary operation on set n of natural numbers. See, whenever we are saying some operation is not a binary operation on certain set, then in that case it is enough to give one counter example for which it fails. So if I consider 2 and 3 and add them, then 2 plus 3 is then 3 minus 2 is 1, which is a natural number. But if I consider 2 and 3 and I'm doing 2 minus 3, then 2 minus 3 is minus 1, which is not a natural number. That means for every pair of A and B belonging to n, A minus B is not necessarily a natural number. So it holds only if A is greater than B. But for A less than B, A minus B is negative number, which is not present in natural number set. So we can say that subtraction is not a binary operation on n. Here we have considered instead of 2 and 3, 5, 8. Same thing happens. 5 minus 8 is minus 3, which is not a natural number. Now see, here star is defined in quite different way. So an operation star defined on Z as A star B is A plus B minus 2. AB in Z is again a binary operation on Z. First see what is the meaning of this binary operation. It is not our regular addition, subtraction, multiplication, division like that. Here star is defined as A star B is A plus B minus 2. For example, if I consider A is 3 and B is 4, then 3 star 4 will be 3 plus 4 minus 2. So it will be 7 minus 2, which is 5. So in this way, A star B is nothing but first number A plus second number B minus 2 according to definition of star. Now see, for any two integers A and B, A plus B is again an integer. And if we subtract 2 from that integer, then definitely it is an integer. And so this star is a binary operation on Z. So these are some examples. So finally we can say that for any two elements present in that set, if we are applying star on the two elements, then A star B must be an element of that set itself. Then only it is a binary operation. And if you are getting at least one pair AB from that set for which A star B is not present in that set, then it is not a binary operation. Now, these are some remarks from definition. If star is a binary operation on a set G, then first, exactly one element is assigned to each ordered pair of elements of G. That means for any pair AB belonging to G cross G, A star B, that is the only one answer. Then second, the assigned element must belong to the set G. So whatever is the answer of A star B, it is again an element of G. Third, to prove the property, we should prove it for general elements. Then it means we cannot take the elements like 2, 3 if the set is natural number set. Whenever we are proving it in general, then we have to take general elements, arbitrary elements like A, B, X, Y, etc. But to disprove, it is enough to find the elements for which the property does not hold, as we have seen in this example 6. As here the property fails, instead of taking A and B, we have taken specific numbers for which the property fails.